This week, we'll be taking a look at electromagnetic waves and how they have unique traits. An electromagnetic wave is a disturbance in a field. Did you know that you are surrounded by thousands of waves at this very moment? Waves fill every cubic centimeter of the space around you. They collide with or pass through your body all the time. Most of these waves are invisible, but you can perceive many of them. Light is made up of these waves, and heat can result from them. Whenever you use your eyes to see or feel the warmth of the sun on your skin, you are detecting their presence. These waves also allow radios, TVs, and cell phones to send or receive information over long distances. These waves have the properties shared by all waves, yet they are different from mechanical waves in important ways. The second type of wave is called an electromagnetic wave. An electromagnetic wave is a disturbance that transfers energy through a field. Electromagnetic waves are also called EM waves. A field is an area around an object where the object can apply a force, which is a push or a pull, to another object without touching it. You have seen force applied through a field if you've ever seen a magnet holding a card on the door of a refrigerator. The magnet exerts a pull on the door, even though it does not touch the door. The magnet exerts a force through the magnetic field that surrounds the magnet. When a disturbance occurs in a field rather than in a medium, the wave that results is an electromagnetic wave. How do EM waves form? EM waves come from atomic particles that are electrically charged. Because of their charges, these particles can exert a force, it's a push or pull, on one another through an electric field. These particles also create the magnetic fields that make magnets work. When electrically charged particles move quickly, they can start a disturbance or vibration in their electric and magnetic fields. The fields vibrate at right angles to each other, as shown in the diagram above. The EM wave travels in the form of these vibrating fields. As you read in Chapter 1, all waves have the properties of amplitude, wavelength, and frequency. In an EM wave, as the diagram shows, both the electric and magnetic fields have these three properties. Sources of EM waves. Many of the EM waves present in the Earth's environment come from the sun. The sun's high energy allows it to give off countless EM waves. Other stars give off as many EM waves as the sun, but because these bodies are so far away, fewer of their EM waves reach the Earth. In addition to the sun, technology is a source of EM waves that humans use for a wide variety of purposes. When EM waves enter a material, the material often responds by giving off more EM waves. Many EM waves in the environment are given off by the surface of the Earth in response to EM waves from the sun. Electromagnetic waves can travel in a vacuum. The transfer of energy in the form of EM waves is called radiation. Radiation is different from the transfer of energy through a medium by a mechanical wave. A mechanical wave must vibrate the medium as it moves, and this uses some of the wave's energy. Eventually, every mechanical wave will give up all of its energy to the medium and disappear. An EM wave can travel without any medium at all, that is, in a vacuum or space of empty matter, and does not lose energy as it moves. In theory, an EM wave can travel forever. How EM waves travel in a vacuum. Because they do not need a medium, EM waves can pass through outer space, which is a near vacuum. Also, because they do not give up energy in traveling, EM waves can cross the great distances that separate stars and planets. For example, rays from the sun travel about 150 kilometers or 93 million miles to reach Earth. Rays from the most distant galaxies travel for billions of years before reaching Earth. In a vacuum, EM waves spread outward in all directions from the source of the disturbance. The waves then travel in a straight line until something interferes with them. The farther the wave moves from their source, the more they spread out. As they spread out, there are fewer waves in a given area and less energy is transferred. Only a very small part of the energy radiated from the sun is transferred to Earth, but that energy is still a great amount, enough to sustain life on the planet. The speed of EM waves in a vacuum. In a vacuum, EM waves travel at a constant speed, and they travel very fast, about 300,000 kilometers or 186,000 miles per second. In 1 second, an EM wave can travel a distance greater than 7 times the distance around Earth. Even at this speed, rays from the sun take about 8 minutes to reach Earth. This constant speed is called the speed of light. The vast distances of space are often measured in units of time traveled at this speed. For example, the Sun is about 8 light minutes away from Earth. The galaxy shown in the photograph is 60 million light years from Earth. Electromagnetic waves can interact with a material medium. When EM waves encounter a material medium, they can interact with it in much the same way that mechanical waves do. They can transfer energy to the medium itself. Also, EM waves can respond to a change of medium by reflecting, refracting, or diffracting, just as mechanical waves do. When an EM wave responds in one of these ways, its direction changes. When the direction of the wave changes, the direction in which the energy is transferred also changes. Transferring energy. A mechanical wave transfers energy in two ways. As it travels, the wave moves more potential energy from one place to another. It also converts potential energy into kinetic energy by moving the medium back and forth. In a vacuum, EM waves transfer energy only by moving potential energy from one place to another. But when EM waves encounter matter, their energy can be converted into many different forms. Converting energy from one form to another. How EM waves interact with a medium depends on the type of wave and the nature of the material. For example, a microwave oven uses a type of EM wave called microwaves. Microwaves pass through air with very little interaction. However, they reflect off the oven's fan and sides. But when microwaves encounter water, such as that inside a potato, their energy is converted into thermal energy. As a result, the potato gets cooked, but the oven remains cool. Number one, a device on the oven produces microwaves and sends them toward the reflecting fan. Number two, microwaves are reflected in many different directions by the blades of the fan and then again by the sides of the oven. Number three, microwaves move through the air without transferring energy to the air. Number four, microwaves transfer energy to the water molecules inside the potato in the form of heat, cooking the potato. EM waves usually become noticeable and useful when they transfer energy to a medium. You do not observe the microwaves in the microwave oven. All you observe is the potato cooking. In the rest of this chapter, you will learn about different types of EM waves, including microwaves, and how people use them.